Hello, I'm Katayun Barmak in the Department of Applied Physics and Applied Mathematics at Columbia University. And today I would like to talk to you about automated grain boundary detection for bright field transmission electron microscopy images. The experimental platform for our studies is metallic thin films. We make these thin films by sputter deposition in an ultra-high vacuum system, and we study them primarily in a transmission electron microscope, scanning transmission electron microscope. The samples for our study are polycrystals, and the reason we're interested in polycrystals is that most technologically useful metals and ceramics are polycrystalline microstructures composed of a myriad of small monocrystalline grains separated by grain boundaries. And here on the left, I show you a bright field transmission electron microscope image of an aluminum thin film. And this is direct space information, and we've collected the image in bright field. So we've selected a direct beam and excluded the diffracted beams. And consequently, that allows us to get contrast. So you can see the polygonal structure of the material, so grains and then the grain boundaries. But also because of the mode of imaging, we see contrast within the grain. So there's the diffraction contrast and these bend contours. On the right is a scanning transmission mode collection. So reciprocal space information is collected, which is at each point we have a small nanobeam, we collect the diffraction pattern, and it's a scanning beam, so it's a point-by-point image, by contrast to the image on the left, which is recorded instantaneously and simultaneously. The advantage of the mode of imaging on the right, which is precession electron diffraction method, or a 4D STEM technique, is that we get crystallographic information. Today we'll be focusing on the parallel beam imaging. Grain boundaries play a very crucial role in determining the properties of materials across a wide range of scales. So they heavily affect the properties, and here I show one example. In integrated circuits, the interconnects have been copper since the mid-1990s, and as Moore's law scaling has dictated, the dimensions of these interconnects have been shrinking. And so that as the thickness, the width, and the height of the interconnects, particularly closer to the transistors, is diminished, we get closer and closer and even below the electron mean free path. And all the grain boundaries within these polycrystalline copper interconnects scatter the electrons and cause an increase in resistivity. Resistivity is at the macro scale, a scale-independent property, but as you go close to the electron mean free path or the phonon scattering length, you begin to get this additional scattering from features such as grain boundaries. And here, as you can see, the grain boundaries dominate the resistivity increase. So we're interested in polycrystals in engineering the grain structure, and one method by which we engineer the grain structure is through grain growth or coarsening of a starting structure. Here I show two snapshots of a simulation where, in going from the left to the right, the structure has coarsened. The reason that the structure coarsens is that the grain boundaries, which are the boundaries you see in these snapshots, are defects. They impure materials, they represent regions of higher energy because the atoms at the grain boundaries don't have as many near neighbors as within the grain itself, and therefore there's a sort of a broken bond associated with the grain boundary, and so they're at higher energy. These grain boundaries are not equilibrium defects, and upon annealing, this structure coarsens so as to reduce the total boundary area, and that's what you see here. As we just said, structures coarsen as we elevate the temperature and give the atoms mobility. However, we do not yet have a predictive theory for the evolution of the grain boundary network in real materials. And to illustrate this point, I show you the plot in the middle section of the diagram, where you see the probability density for the so-called reduced area, in other words, grain area normalized by the mean area plotted. And the data in the black is from the experiments, just such as from the images that you see on the right. And the open circles are from the simulations, which are mean field simulations and for isotropic boundaries, meaning all boundaries are the same. In real materials, all grain boundaries are not the same, but you can see the very distinct disagreement between simulations and the experiments, just by way of illustration. So here, the data was collected from these experiments manually by hand, because at the time we did not have automated methods for tracing these grain boundaries. We'd like to automate that, and that's what we've been after for a very long time. We also, up till now, recently have not had quantitative in situ parallel beam imaging of grain growth in thin films, which would allow us to see the evolution of a grain structure dynamically. So we really need automation, and as I said, we've been after it for a very long time. We recognize the need for automation, meaning tracing the boundaries in an automatic way, back in the 1990s, and we did succeed then with a C++ code to at least automatically trace some the images that we collected at that time and plot the probability density here for the grain diameters, both by hand and compare it with the automated tracing. And at that time we found good agreement and were very excited. However, the methodology developed then and the C++ code really had limited success, meaning it did not generalize, it only worked for those set of images. So could not be used again. Revisited the problem in the 2000s with now more sophisticated, more mathematically sophisticated edge detectors, and tried again and on various sets of images and found that the code again worked on some images, didn't work on other images, and simply just did not work well enough to for us to even publish a manuscript, and we abandoned the effort again. Then came the revolution of the computer vision in the 2010s and all the convolutional neural networks that then exploded on the field. And the convolutional neural network that now is used quite widely in material science, and we have also now found useful for our problem, is the so-called UNet convolutional neural network, and it's so named because of the shape of the network, which is a U. It has a downward arm, descending arm, the encoder arm, and then an upward arm, which is the decoder arm. It uses limited but dense training data, so it's advantageous for us where we also have limited data. It can work on touching objects of the same class, and the particular class for which this network was developed were stained biological tissue that was imaged in bright field TEM. These images had internal contrast, again, because the samples were stained, but the contrast was mass thickness contrast, whereas we have diffraction contrast, which generates particular issues. No matter, all neural networks need training, and training needs ground truth. And for the types of images that we have, the ground truth happens to be the subset of the images and the tracings, the hand tracings that we now have available and have made use of. And as you can see, these are the samples of aluminum, and what you see here are scanned negatives. These are photographic plates, and the sample has had to be tilted so that we change the diffraction contrast so that maybe some grain boundaries that could not be visualized in one sample tilt could be seen in another sample tilt. Then by hand, boundary by boundary, this data is amassed to generate this network that you see down here. The boundaries of the grains that touch the field of view were not traced because we were not going to use the data from those grains in our grain size distribution. The other feature of all these tracings that we use for training is that these traces way back then had to be verified by a second observer. In other words, two people had to agree that in any one location there was a grain boundary. And if there was not agreement, those grains and the boundaries would not be included in the data. So that's why the data is actually being verified. But as you can see, because we have to tilt the sample, there was always image shift, and these images are not aligned. And so for training, we do have to manually align every image and tracing. This was done. However, the data is really not very useful as it is in these tracings for the training. So we had to come up with a slightly different approach. And what we did was select patches from the images and tracings. And these patches could be overlapping because they represent new data for UNet for training. And these patches also needed to then be scaled to 256 by 256 pixels because of the particular UNet version that we were using. However, we also did augment the data by 90-degree rotations and reflections. We did not deform the grains as they did in the original UNet development, because that is not the form of deformation that was applicable to our samples. And these, therefore, in the training, we only use reliably traced regions. And as you can see, these are two patches from the same field of view, but they count as two different training data sets. The UNet output is not immediately the full trace boundaries. What you get is a grayscale image. And here you see the 3 grayscale images for the 3 sample tilts in this aluminum sample. These tracings from the UNet then have to be compiled. Then we apply a double threshold in our post-processing approach. We have found that a single threshold did not work even back in 1998. Then there is a dilation. So these are the other morphological operations, the dilation, the closing of the holes, which would be grains that are too small to be physical, skeletonizing, and then some kind of pruning because we have these dangling segments, and then and only then do we use these post-process tracings for collecting grain size data. And here we show you the comparison of bright field images for hand tracing, hand traced images, and here's the UNet processed. The grain centroid in the UNet output and in a hand tracing are much closer than random, so these are reliably this grain is this grain. We verify that. And then we need a statistical comparison because, as you can see, although they are very close, they are not identical boundary tracings. We used 3 different statistical tests to see that they collected data by way of, again, the probability density for the diameter normalized by the mean diameter is statistically equivalent, and indeed we find that to be the case, and that allows us to then accept the parameters that we optimized for the UNet. Now, of course, that's the trained model and validated, but now we need to test on new data. In other words, we need to test whether the UNet that and the way we have trained it is generalizable. So we are using now new aluminum samples recently deposited, and we optimize the post-processing. We use the same model as for the old data, but we need to optimize the post-processing parameters because the types of images we get now have a very different contrast profile than the old images. And these we still therefore require some minimal amount of machine-assisted hand tracing, meaning we use some of the network from UNet and then augment it with the human tracings. And we then collect now, because it's now automated, much larger data sets from a given sample, and we can see that the grain size distribution again is not significantly different, and therefore the UNet model that was trained on the old aluminum data works also for the new static, meaning ex situ aluminum data with no additional training. However, our interest is really in going to dynamic data collection. So we would like to run the experiments in situ, and I'm trying to get the, not sure why the movie is not working. And collect the data while it is running dynamically, and watch the grains grow. So here we are also taking advantage of the developments in the sample holders, which make use of microelectromechanical systems and allow for very small thermal mass with the heater incorporated inside the chip. And however, because this is now going to be dynamic data, we need to revisit the way we image. So before, for static images, we were tilting the samples. And however, this tilting of the sample causes, even when you're at the eucentric height, large and abrupt image shifts. So it's not useful for doing the dynamic experiments. So we've changed the mode of imaging. So instead of tilting the sample, we're tilting and rotating the beam. This gives us small, smooth image shifts. So therefore, what we are using is a conical bright field imaging mode. We then generate, for the in situ data now on platinum, different type of material than aluminum, we generate some hand tracings because, again, we need to re-optimize the network. And what we do is what is known as a transfer learning approach. In this transfer learning approach, we start with the original model with weights for aluminum. We retain the encoder arm, but then retrain the decoder arm on the platinum data, which has the tracings that we can use for training. And then we go back and fine-tune the entire network for platinum, and we have to do the optimization of the post-processing parameters after UNet, and that uses two tracings from the in situ heating experiments. So you still need some minimal expert data, meaning human tracing, but it is now very minimal compared with the old approaches. So we've done this transfer learning for platinum, and we can now go and look at the dynamic data, and we take advantage also of the developments in computer vision that allows us to, with the protochips Axon, get the drift correction so that all our images are aligned, at least for some period of time that is relevant to our experimental span of time. And as you watch here, this is the movie as the grains are growing in platinum at an annealing temperature of 800 degrees C. And at the same time, we are able to now superimpose the boundary tracings from UNet. And if you go back to the original image, you will see that the grains have indeed grown. And so we will then extract these tracings and then use them for model development. We still need to improve the segmentation, but we have come a very long way since 1998. So, in summary, the grain growth data can be collected at unprecedented time resolution because of the advances in hardware, not just the microscope and the detectors, but also these wonderful holders. There is very great advances in software and in image processing. And for quantitative analysis, we have found UNet to be a very powerful solution, but of course there are more solutions coming on board all the time now. It's an exploding field. And we have shown that the UNet model that we have trained is can be used on other materials. And here we showed the platinum data. We have also applied the model directly to palladium. And here is palladium, so another face-centered cubic elemental metal, but certainly different than aluminum and platinum. So I'd like to acknowledge the many undergraduates who worked on this project. And the one under the graduate student Matthew Patrick and my colleagues, Professor Levine and Rickman. The work has been published, and here is the reference. And I'd also like to acknowledge the National Science Foundation, who's funded us on a number of grants.